This section takes a look at the basic concepts of probability and why probability is so important in statistics. And we all have an intuitive sense of probability. When you flip a coin, if we said, what's the probability of flipping a head? We all know it's 1 out of 2, 50% probability. But what we really want to do is delve in deeper and define what is probability and how we can use it in statistics. So maybe the first thing that we might need to do is figure out if we can finish the sentence. In that, if I asked you what probability is, can you finish what probability is? So one definition of probability, or use of that word, is probability is the branch of mathematics concerning numerical descriptions of how likely an event is to occur. So often we want to figure out how likely something can happen. So for instance, let's say you're a drug manufacturer making a new, let's say, vaccine to cure people of some unknown virus. Suppose you have this drug and you test it on, let's say, 300 people, and after a week or two, we find out that 190 of them have been cured of the disease. So the question is that 190 out of 300 a lot of people or not very many people? So what we might say is, well, suppose the drug did not have any effect on curing this disease. What's the probability that if it had no effect on the disease, what's the probability that 190 out of 300 would have been cured? Is that a likely event or an unlikely event? And what we can then do is make a decision on whether that drug was effective or not. So that probability is really a branch of mathematics, but there's another description of the word probability. In that, we can say that the probability of an event is the likelihood of that event occurring, and is always between 0 and 1 numerically. So 0 and 1 really means 0% and 100%. So if a probability of an event is 0, we call that an impossible event. It's just not going to happen. And the probability of 1, that's a certain event. It's 100% going to happen. That's an event, or a certain event. So probability, kind of two different words to it. One is it's the branch of mathematics. Two, we all know what it means to calculate a probability, like flipping a coin where 50% head, 50% tail. There. I also kind of consider probability as almost a language, in that it's part of the language of statistics there. So we really want to understand a lot of the concepts of probability. One that you might already see is this term event. We use this word event quite a lot on here. So question is, what's an event? And there's really a couple of different types of events. The first one is, what's a simple event? So what's an example of a simple event? So one example might be the event of a puppy being female. So if you had a litter of puppies, and you randomly chose one, what's the probability of that particular puppy being a female? So that's a simple event. Another example of a simple event might be the event of making 7 free throws in a row. There's only one way to do that, and that is to make all 7 free throws in a row. So those are both examples of what a simple event is. So what's an example of not a simple event? So what's not a simple event? So suppose we had the example of, let's say a couple has 2 children, a boy and a girl there. So is that a simple event? A couple has 2 children, a boy or a girl. Well, in this case, this is not a simple event because there's actually 2 ways you could have a boy and a girl. One way would be to have the boy first and then the girl, or the girl first than the boy. So there's actually 2 possible ways. And these are different because in this first case, you've got the older child, let's say, as a boy and the younger as a girl. Or in the second case, the older person is a girl and the younger child is a boy. So 2 totally different ways. So a lot of times we call this a compound event, in that it's not simple. There's more than just one way to do it. So think of simple as being one way the event can happen, and a compound event, or not a simple event, is at least 2. There. So now, Another important term that we want to take a look at is a sample space. What is a sample space? So a sample space is really the collection of all of the simple events. So if we wanted to think about the sample space of a couple having two children, well, we've already written down two ways that it can happen, a boy and a girl, and then a girl and a boy. There's actually two more possibilities with two children. You could have a girl and a girl, or a boy and a boy. And if we write all of those different simple events down, we've got what's called the sample space. So let's look at another example of what a sample space might be. So suppose we want to find the sample space of flipping a coin 3 times and figure out in terms of did we get heads or did we get tails? So we start by writing down S for the sample space, and it's a set, so we'll write down a squiggly brace. So S is the set. Well, one way to get flip 3 coins would be to get a head, and a head, all 3 heads. Now, another way is possibly if we got a tail and then a head and a head. But now that tail could land on either the first, second, or third, so we've got some other possibilities for one tail. It could be head, tail, head. It could be head, head, tail. From here, possibly we could get 2 tails. So if we got 2 tails, we could get those on the last 2, let's say. So head, tail, tail, or tail, head, tail. Tail, tail, head. And finally, our last way of flipping 3 coins would be all 3 tails. Tail, tail, tail. So we can see that the sample space of flipping a coin and recording the different ways we can get our head or tail is actually 1, 2, 3, 4, 5, 6, 7, 8. There's 8 different simple events in this entire sample space there. So now let's write down just a generic event. So let's say we wanted to let A be the event of a head, head, or head. Now, this is a simple event because how many ways can we get a head, head, and a head? Well, just one. So this is a simple event. We just get the one way of doing that. Now, let's make another event. Let's say that I want to let B be the event of getting 2 tails. Now, this one is not simple because in our little sample space, how many different ways can we get 2 tails? So we can get 2 tails, we can see 3 different ways. So the 2 tails at the last, on the outside, first and third, or the first 2 flips. So that's not a simple event. There's more than one way to actually get the 2 tails out of 3 flips of a coin. Now, suppose we want to start calculating the probability of both of these. What's the probability of getting 3 heads, or what's the probability of getting 2 tails? Well, the probability of an event, we write it kind of as using function notation, P, or we could say P of A or P of B, since that's how we defined A and B here, but we'll just say the probability of an event. This is the number of ways the event can occur divided by the size of the sample space. Now, this is called theoretical or classical method of probability, and I'll write that down in a second here. But let's first find out what the probability of A is. So what that really means, what's the probability that we flip a coin 3 times and we get 3 heads? So the probability of A is equal to, well, we've got one way that event can happen divided by a total of 8. So 1/8, or if we turn that into a decimal, we would get 0.125, or we could say 12.5%. Now, what's the probability of B getting 2 tails out of 3 flips of a coin? Well, similarly, how many ways can that event occur? We can see that it can occur 3 times out of 8. Turning that into a percentage is about 37.5 on the calculator. So both of those, 12.5% or 37.5%. So this is, as I mentioned, called the theoretical or the classical way of calculating probabilities, in that there is a way to count up everything in our sample space and actually calculate what those percentages are. Now, another kind of probability is what's called the experimental or the empirical method. And this is when you do an experiment. So let's say C is the event of flipping a thumbtack and having it either landing point up or point down. So draw a little picture here. Your thumbtack might land with the point sticking up, or it might land at some kind of an angle. Let's call that sticking down. So there's no way of actually calculating the probability that a thumbtack is going to land up or down. The only way we can figure it out is through a bunch of experiments. So we can run a bunch of trials. So how can we calculate the probability of this event? Well, the probability of C is going to be the number of times event C occurs, and then we'll just divide that by the total number of trials. So, as an example, let's say I'm bored on Sunday. I'm going to flip a coin 300 times. So I'm going to say N is 300. I've got that, or I flip a thumbtack. So I've got that number of trials I'm going to do. And let's say out of flipping my thumbtack 300 times, I get 147 times that it lands up. So I'm going to say X is 147. So the probability of the thumbtack landing up would be the number of ways it occurred, that would be 147, divided by all 300. And if we do that calculation, we get about 0.49 or 49%. So I'm pretty sure that the thumbtack will land point up a little bit less than 50% of the time. Now, to really get a good idea of how accurate this is or what the true probability is, I would have to do this 1,000 times, 10,000 times, 1,000,000 times. The more I do it, the closer it's going to get to the true probability. And that's the law of large numbers. So the more times I run the trial, the more accurate this percentage is going to get. Finally, the last type of probability that we have is something called subjective probability. And subjective probability is if you just make a guess at what the probability of an event might happen. So suppose I said, I think there's 20% probability that it will snow this Christmas there. So there's no way to calculate it using the theoretical or classical method. There's really no way to experiment it because this Christmas is only going to happen once, so there's no way to run several trials on it. So the best I can do is just kind of make a gut feeling on what I think it's going to if it'll snow or not on Christmas. And I just use that from past experience, some prior type of knowledge, just to make a guess as to what the probability is. So that's subjective probability. So really three different types of main probabilities. We've got theoretical probability, experimental or the empirical, and then subjective. Now, another term and concept that we'll be using quite a bit in chapters 5, 6, 7, probably even 8 and 9 is what's called the complement of an event. So, new page here. The complement of an event A is a set that consists of all outcomes in which A does not occur. So, the complement of event A is a set of A that consists of all outcomes in which A does not occur. So what's that really mean? So let's go back to our example of flipping 3 coins. So if A is that set of getting 2 heads in 3 flips of a coin, what is the complement of A? So first, the notation for the complement is A with a bar above it. So the complement of A is not getting 2 heads. So how can we figure out what the probability of not getting 2 heads is? Well, let's go back to the probability of A. So that was the probability of getting 2 heads. And if we recall, that was 3/8. So if there's 3 ways to get 2 heads, well, there must be 5 ways to not get the 2 heads, the other elements in that sample space. So the probability of the complement of A is 5 out of 8. So another way that we could have done that is we've got a little formula here. We could have said the the probability of the complement is really just 1 minus the probability of A. So if we took 1 minus 3/8, we'll get 5/8. So another thing that means is if I do a little algebra here and add the probability of A to the left-hand side, we can also say that this really implies that the probability of A plus the probability of the complement of A is 1, which kind of should make sense in that, kind of go back and think of, I don't know, let's say the probability, let's let B equal that it will rain next Monday. So suppose we said, well, I think the probability that it'll rain next Monday is 25%. So that's my subjective probability. So if I think the probability that it will rain next Monday is 25%, then the probability that it doesn't rain, or the probability of the complement of A, is 0.75, 75%. Does that make sense? It's either going to rain or not rain. There's no other options. So the probability that it rains plus the probability that it doesn't rain has to be 1 or 100%. I'm certain that it's either going to rain or not rain. So we know that the probability of an event plus its complement better equal 1. Where this comes into play at is when we really want to calculate either the probability of the complement of A or the probability of A. It's always going to be 1 minus the other probability that we're not calculating. So let's take a look at one last example to try to reinforce some of these concepts. So here's another example. Let's say I want to find the sample space of rolling 2 die and calculating the sum on those 2 die. So just a simple game with 2 dice, roll them, add up the faces, and we'll play that game. So if I draw a couple of dice here, 1 dice here, we've got the sides 1, 2, 3 showing. Make another dice, maybe a blue dice, and we'll have maybe 4, 5, and 6 showing. So on a normal dice, we've got the numbers 1 through 6 on it there. Now, if we think about what the sample space might be of the sum of adding up the faces that are showing, we could say, well, the smallest you would get is if both dice showed 1. So we might get a 2 for the sum. The largest we could get is 6 on both of them, or 12. So what we might think is that our sample space is just going to be the values 2, 3, 4, 5, 6, 7, 8, 9, up to 12. So what's that, 11 different values in our sample space? But that would be wrong, because suppose I said one dice was 3 and the other dice was 4. So what I've got drawn here is that the green dice is 3 and the blue dice is 4, but we could turn that around. That's not a simple event, because we could have gotten a 4 on the green dice and a 3 on the blue dice. So this is not a simple event type of idea here. What we need to do is take a look at what all of the simple events are. So let's draw a little table here and just keep track of the faces for the blue dice and the green dice. So let's say my green dice can be either a 1, 2, 3, 4, 5, or 6. Let's put that across the top row. Let's say that the blue dice can be also 1 through 6, but let's write that down on the bottom row, or on the column. And now let's make this little table of representing the sum of each of these dice on here. So what we would get is, let's see, a 1 and a 1, that could be 2. 1 and a 2 could be 3. And then 4, 5, 6, 7. And if we fill up this entire table, let me give it a time here. Here are all of the different sums or simple events of rolling 2 dice and calculating the sum. So how big is the sample space actually? Well, we've got 6 columns by 6 rows, 36. So our sample space is actually 36, not just 11 of the numbers 2 through 12. Yes, the numbers do go from 2 through 12, but there are a lot of different ways to get, let's say, a sum of 9. We could get a 6 and a 3, a 5 and a 4, 4 and a 5, or a 3 and a 6. 4 different ways to actually get that event there. So let's do a couple of calculations here. Let's say, let's see what the probability of getting the sum greater than 9. So if we wanted to find the probability that the sum is greater than 9, we can see that, well, greater than 9, don't include the 9s. We want strictly greater than that. So that would be 10, 11, and 12. And we can see that there's 6 different ways out of all 36 to do that. So our probability would be 6 out of 36, or 1/6. There, so there's a 1/6 probability of getting a sum greater than 9. Now let's do one that's a little bit more complicated. How about the probability of getting a sum of 6 or 8? So what's the probability of getting 6 or 8? So here we can see, here looks like where all of the 6's are. Here's all of the 8. So if we circle all of those, count those up, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like we've got 10 ways out of all 36 to get either a 6 or an 8. So 10 out of 36, I'd get 5/18 there. Finally, let's do one last one. How about, let's see, problem C. Let's do the probability of not getting a pair. Wow, probability of not getting a pair. Now that, I would have to look at my table here and figure out which of these elements here, how many of them are not when the dice are the same. But what might be easier is, let's use our complement rule, in that I can see that the pairs are down this diagonal. So 1 and 1 is a 2, 2 and 2 is 4, 3 and 3 is 6, then we have 8, 10, and 12. That's going to be a lot easier to calculate out. So I'm going to use that complement rule, that the probability of not getting a pair would be 1 minus the probability of getting a pair. So how can I calculate that? Well, I can see that there's 6 different ways to get a pair right there. I'm going to erase that. So 6 different ways of getting a pair. There they are. Let's do it that way. So we'll get 1 minus 6 over 36. A couple of ways we could combine these together. I'm first going to get this 1 as a common denominator of 36. So let's write that as 36 over 36 minus 6 over 36. So we've got 30 over 36 by subtracting these two fractions. Or we can reduce that down to 5/6. So the probability of not getting a pair is 5/6. And of course, we could turn all these into decimals, so it's appropriate to either leave our probabilities as fractions or turn them into decimals like we did on the previous ones. So take a look at this section, some of the basic probability concepts, and then we'll jump into actually using these when we jump into Chapter 5.